frequency is how many cycles per second, whereas this is the number of seconds per cycle. So it's reversed. So frequency is measured in like hertz and number of cycles per second. Okay. And what about the amplitude? This is why I brought my trig book. This is the only thing we're going to pull from it. So the book does all this fancy stuff. They write it as a single cosine function, and it's got some phase shift involved. They talk about that. I don't care. I don't care about the phase shift or anything like that. Okay. But one thing we can pull from this is amplitude. Now I have a sum of two, cosine and a sine function, but they share the same period. That's the important thing. If they share the same period, then you can write this as a single function, and all I want to take from it is what would its amplitude be? I have to do research. I remember it vaguely, but I don't remember it off the top of my head either. So if you look at this, provided their periods are equal, the sum of a sine function and a cosine function can be written as a single sine function or cosine function like the book did. So you got A1 sine beta t, we just call it omega, plus A2 cosine beta t. Then you get this giant, you could write it as a single sine function. It involves the sum of sine functions up here, sine of a sum, all that. Anyway. But that amplitude of the new function turns out to be square root of the sum of the squares of the original amplitudes. It's almost like, this is awesome because it's almost like finding, as if A1, A2 is a vector quantity, it's finding the magnitude of that. A1 squared plus amplitude of the first one squared plus amplitude of the second squared, added together, square rooted. Okay? So that's almost like if A1, A2 were a vector, that's the magnitude of that vector. All right, so that's part of the thing. They do talk about it in the book, but we're not going to go as far as our book does. The amplitude, it'll be square root C1 squared, that's what we're calling it here, plus C2 squared. Okay. So that just talks about the total distance from equilibrium that it goes on either side, that mass will go on either side of it. Okay. All right. So we got some other situations to talk about. So we just talked about one, undamped motion. So that's if we ditch that dash plot altogether. Okay. Now we're going to consider that dampening force. Dampening force? Okay. So, case 2. Damped motion, and that's if we do have a dash pot. In other words, that constant is not 0.
Will you focus it one more time?
Oops.
Thank you.
All right. So I'm just going to write down the full equation again. Mx double prime plus Cx prime plus Kx equals 0, right? Okay. So again, dividing through by m gives us x double prime plus c over m x prime plus k over m x equals 0. Again, those are just constants, c over m, k over m. And it cleans things up later if we're going to call this constant c over m, instead of calling it just like p, they make this strange substitution and they say, okay, for a second, we're going to call that 2p. It's going to make calculation later on cleaner. Okay. And k over m, I think we called that omega naught was k over m. So k over m by itself could be written as omega naught squared, right? Okay. So we got these things over here where 2p equals c over m. So p would be c over 2m technically. We're just holding on to it for a second. It's going to make some calculations nicer. And omega naught squared, omega naught was the square root of k over m. Okay? So omega naught squared is that k over m. All right, so what would the characteristic equation be from this? Yeah, if we made that assumption, okay, it's linear, second order with constant coefficients, we would say assume x equals e to the rt. Then the resulting characteristic equation, second derivative is alone, so I'd have r squared plus 2pr.
Plus omega naught squared.
Yeah, plus omega naught squared because the x to the first, or there's no derivatives there, so we factor out the e to the rt. We have omega naught squared equals 0. Okay. All right, so this is quadratic in R, and so we could use the quadratic formula. So R would be equal to, using the quadratic formula, opposite of that coefficient, so it would be negative 2p, plus or minus square root of that squared, so that's what, 4p squared, minus p squared minus 4a, leading coefficient is 1, c, and that's omega squared, omega naught squared. Okay, all over 2 times a, so that's 2. All right, we're going to clean this up a little bit. Negative 2p plus or minus square root 4p squared minus 4 omega naught squared. This is why we made that substitution for 2p all over 2. So I'm going to break it down. Negative 2p divided by 2 plus or minus. Now there's a 4 in both of those terms. So you can factor that 4 out, and the square root of 4 is going to pop out of there. I'll have 2 root p squared minus omega naught squared. All over 2. That's why we did this. These cancel. So do those. And we just get negative p plus or minus square root p squared minus omega naught squared. Okay. So that's R. Now, there's going to be some distinctions here based on the sign of what's under the radical. Yeah? So this naturally kind of breaks this into 3 other cases. So in this case, damped motion, we got 3 subcases. According to the sign of that part under the radical. Okay. So this will yield 3 subcases. All right. So let's look at the first one. Oh, by the way, I'm going to call this star, just for reference. Okay, just that equation for R. So case A. What if that part under the radical, p squared minus omega naught squared, is positive? Okay. So then the square root of a positive quantity is going to give us two values, right? Two solutions.
Two real solutions.
We're going to have two real solutions. And let's explore that a little bit. So just again, to expand this p squared minus omega naught squared, remember what we call p was c over 2m. So p squared minus, and omega naught squared is just k over m. Okay? So, simplifying this, getting a, what am I talking about? That's c over 2m. I put 2 over c in. All right, so we get c squared over 4m squared minus k over m. Get a common denominator. I don't need to multiply 4m, numerator and denominator. So 4mk. Okay. So, with this calculation or formulation, saying that p squared minus omega naught squared is positive is absolutely, what's it called? What's the word I'm looking for? What does this arrow mean? It's been a long day. What? It's an if and only if. Synonymous? What's the word for that, man? Equivalent. Yeah. Right, equivalent. So, saying that p squared minus omega naught squared is greater than 0 is just equivalent to saying that the numerator is positive, right? The denominator is always positive. So it's just saying that it's equivalent statement to say c squared minus 4mk is greater than 0, which is totally equivalent to saying that c squared is greater than 4mk. Okay? So this is what they call overdamped system. Okay? If c squared is greater than this 4mk, the critical spot is when you get a 0. So if c squared is equal to 4mk, that's what they call critical damping. So we got this sort of one situation that breaks it up. Right? If c squared is greater than 4mk, then it's positive. If c squared is equal to 4mk, then this is 0. Right? And we have one solution. If c squared is less than 4mk, then I'm going to have a negative under the radical. So that part sort of separates it. Okay? C squared equal to 4mk separates it. Now, so this is what they call overdamped. And we'll see why when we get the solution for this. All right, but yes, there will be two solutions, two real solutions, because I got two real roots to that critical or that characteristic equation. All right. So putting this back into what that equation star tells us is that we get two distinct real roots. Okay, so negative p plus or minus square root p squared minus omega naught squared. Okay, so this is two distinct real roots. Okay. All right. So the solutions, right? X will be e to the r1t. The other solution would be e to the r2t. And any linear combination of those serves as the general solution. So x of t can be written as c1 e to the r1t plus c2 e to the r2t And these, I'm not going to put them in there, but yeah, when you get real numbers, and it just happened they could be irrational. Okay. All right. Now, I'm not going to go through this, but it can be shown that both R1 and R2 will be negative, which we'll see should make sense. They should be negative. All right. Now, if we were given some initial conditions on the position of the spring, so if they said at time 0 the position of the spring is 3 centimeters, or whatever it is, okay, that would be an initial condition, x of 0 equals 3, and when it is let go, the velocity is negative 5 centimeters per second. That would be an initial condition involving x prime of t, its velocity. So if we have initial conditions, we could recover those coefficients and get the exact function for, position at time t.
Is that a negative c, or is that just a dot?
That thing is, I don't know what it is. It's like it's just a piece of fuzz. I can't get off the paper. Something wrong with the paper. No, it's just a C1. Okay. C1 plus C2. Okay. So if R1 and R2 are both negative, what would be happening to x of t as t goes on to infinity? If these are negative, if we believe this, right, it would be going to approaching 0. Okay, which makes sense. Why? Right, it's dampening it. Now, overdamped, you could argue that, well, maybe it never reaches 0. If you let go, it's dampening so much that it never passes its equilibrium position. It just slowly approaches it. Okay. Take a look at your books if you got one. I'll flip it open too. Page 340, not page 347, page 191. Figure 3.4.7 right here. So this one right here is the overdamped system. All right. So they all are saying, initial position x naught. So they're giving you several graphs that have the same initial position at time 0 with different initial velocities. So initial velocity positive, which means somehow it's stretched to the right and yet moving to the right when you let it go. So I don't understand that graph so much. If you shove it and let it go, I don't know, and it was still going to the right somehow. All right, so this is the critically damped. What happens is it quickly returns towards the equilibrium. There's not no oscillation. Okay, that's why it's called overdamped, right? So you could get different graphs, but they're not sinusoidal in nature. What other case could we have? So our cases were broken up in part 2. So 3 subcases. The first one, p squared minus omega naught squared could be greater than 0. What's another case about that? The radicand there. What else could it be?
Less than 0?
Could be less than 0, or it could be equal 0. Those are the only 3 choices, the only 3 possibilities. So we're just going to go right down the ladder. We said, okay, let's take a look at when it's positive. That gives us the overdamped case. So it corresponds to a great force from the dashpot. Slows down that oscillation. Well, really, there's no oscillation. Okay, it just goes right back to equilibrium. So the second case we're going to look at is if this vanishes. In other words, if p squared minus omega naught squared is 0. that quantity of the radical, p squared minus omega naught squared equals 0 right on the nose. This is the one that they say is critically damped. All right. So if that drops out, then what does our equation look like? Or the characteristic equation?
Negative p.
Right. We get one solution. So saying that p squared minus omega naught squared equals 0 is equivalent, when we broke apart what that means, p naught squared minus omega naught squared, that's if c squared equals 4mk. Okay, the book does it in a slightly different way. They talk about that critical value for C where you get a 0. So they put it in terms of C. This happens when C squared equals 4mk. This is the critical damping. Okay, so the way the book puts it, I think, is they call it C sub CR, critical, square root 4mk. We don't really deal with those in the situations. They just say, oh, if it's critically damped, what's it going to do? If it's over damped, what's it going to do? But this is the breakdown. Okay. So from equation star, that was the characteristic equation, we just get R1 equals R2 equals negative P. Okay, our characteristic equation in star here, if this drops out to 0, we get negative P. And since it's a solution to a quadratic, it's a repeated solution. It has multiplicity 2. Right. So there was a case when we get a repeated root, our solution to the original differential equation would be
C1
e to the negative R1t, and I'm just going to call them both R1 for a second. Oops, just R1t, it's already negative. Plus C2, and if it's repeated, we get a linear factor out front. Okay. So factoring out that e to the r sub 1t, we get C1 plus C2t. That's the linear part. Now, our solution for R1 both and R2 was negative p. So we get e to the negative pt, C1 plus C2t. That's the solution for the critically damped case. So that wasn't too hard to get to. So let's make some notice a couple things about this, the characteristics of this solution. What happens to x of t as t goes to infinity? Because we got e to the negative pt, so whatever's in here doesn't matter. This factor is asymptotically going to 0, right? So it doesn't matter what's in the parentheses. That factor out front is approaching 0, so x of t goes to 0 as t approaches infinity. Okay. Another thing, the spring, according to this equation, the spring can cross its equilibrium position at most once. Why is that? What about that equation tells you that? Right. So equilibrium position is when x of t is 0. This part never equals 0. So it has to come from here. So if you have a linear part, there's only one value of t that would solve that. Okay. Now, why do I say at most and not exactly 1? We're starting this system at t equals 0, so the domain would be just positive t values.
C1 or if C1 isn't 0, then it never reaches 0.
Well, I don't know about that, but yeah, maybe the solution C1 and C2, the signs are such that the solution to the equation C1 plus C2 t equals 0, you set it equal to 0, maybe the only solution for t is negative, and so it doesn't have any realistic, doesn't describe anything realistically. Okay, so I'll say at most once, and that would be the solution when t makes this factor 0. So it will cross its equilibrium position at most once, and then go back to, then settle, asymptotically back to equilibrium. Okay. All right. So one last case, and this is 2c. Again, to go back, these are our 3 cases involving p squared minus omega naught squared under the radical. Okay. So our last case concerns that. All right, and which one did we not consider yet?
P minus W squared is
Less than 0.
Right.
Okay, so last case, p squared minus omega naught squared less than 0. Okay, and this is what they call underdamped for some reason. Under, because this quantity is less than 0, that's one way to remember it, I suppose. Underdamped. That quantity is under 0. Okay. All right, so when if p squared minus omega naught squared is 0, then equation star, the characteristic equation gives, what is it? R1, R2, our 2 solutions are negative p plus or minus square root p squared minus omega naught squared. Right? Now, the problem is, if p squared minus omega naught squared is less than 0, then what are we dealing with here?
I times the absolute value of that.
Right. So we are going to have complex solutions. Not just imaginary with a real part 0, but complex solutions. Okay. So this is negative, of course. So what we get is negative p plus or minus, and pull out the square root of -1, that's our I, and then it would be times square root of the absolute value of that. Now, if this is negative, then I could just flip its order, multiply it by -1, it would be omega naught squared minus p squared. Yeah, so that would be its absolute value. All right, so we have 2 complex solutions. And again, we're just going to jump from here to the solution when we have complex values. Okay, but for a moment, I'm going to call the square root of this whole thing, because I don't want to write it in the argument of a function. Call this our new omega 1. So our solution would be, for R1 and R2, negative p plus or minus I times omega sub 1. All right. So our solution for x of t is going to be, oh, by the way, this is our real part of the imaginary or complex number. This is the imaginary part. So the solution is e to the real part times t. And in parentheses, we still get the cosine and sine.